Good afternoon, everyone. I hope you're having a good Thursday. Mixing up the days here. Um, I am. I gotta be honest with you. Just like I think it was yesterday, I brought my lunch to class. But today the lunch is a little bit less invasive, so hopefully it won't be too distracting for me. Um, Part of it is a Rice Krispie treat because Rice Krispie treats are fantastic. All right, so I have been writing your exam, and I'm going to share tomorrow kind of a breakdown of where everything's coming from. And I'm also working on the practice exam. I think what I might do with the practice exam is just start releasing it, or sorry, make it available, but then constantly be editing it. So I'll be adding questions kind of gradually. Right now, I've got 5 questions on the practice exam. And I got to be honest with you, what you should expect for your exam and the practice exam is kind of questions that chronologically follow what we've done. So the very first question on the exam, chances are it is going to be, and the only reason I say chances are is because I'm like 99% sure that Canvas won't shuffle the questions around, but I'm not 100% sure. Um, but I have written the questions to correspond to like the first day stuff. So I think later today, what I'll do is I'll just publish that exam, that practice exam, and you guys can have access to it. Take that as many times as you want. Well, let me clarify, 99 times. Um, and should you need more than 99, let me know, and I think I can either reset it or I can go higher than 99. But later today, I'll publish that, and then I'll continuously be working on it, so you'll see more questions added to it. Um, and then tomorrow, I'll go into more detail about what the exam's over. Okay, so with that in mind, um, where have we been this semester? We started out with kind of a general discussion of some elements from biology, from chemistry. Then we went into water and talked about acids and bases, strong acids. Well, really, we talked most about weak acids. And weak acids because they're kind of the most relevant to us as biochemists. Then after that, we started talking about our amino acids when we looked at the classifications of our amino acids, which we came up with basically 3 big groups, you could argue 2 big groups. We had polar amino acids, non-polar amino acids. The third group was our aromatic amino acids. Those aromatic amino acids, 2 of them are going to be non-polar residues, and then the other one that is an aromatic that is, well, not polar is going to be, or sorry, not non-polar is going to be a polar amino acid. Did I say that? Okay. Um, so we've got those amino acids. Then what we did, and we focused a lot on those amino acids, was we looked at their R groups and how they change, how they are ionizable, how their protonation state changes, and what are the implications of that protonation. Does that amino acid adopt a positive charge, or does it become a negatively charged amino acid? Which relates back to our classifications where we said polar amino acids, that big group, also had there's polar charged positively, there's polar negatively charged amino acids, and then there's polar uncharged amino acids. So those were our big groups of our amino acids. And as soon as we had those building blocks for proteins, our proteinogenic amino acids, then we started talking about the organization of proteins. Our first, most simple level of protein structure is our primary structure, which the primary structure is stabilized by peptide bonds. A peptide bond is never going to have a positive charge because it's got partial double bond characteristic, meaning, and that partial double bond characteristic is from the fact that it is resonance stabilized. Our next level of organization was our secondary structures. With our secondary or our local structures, those are stabilized by backbone hydrogen bonding. They fall into 2 major categories, your alpha helices and beta sheets. We talked about kind of the organization of those and how they look different and maybe even The prediction, which was done by Chow and Fassman, who categorized every amino acid and they gave them all propensity scores. This amino acid is likely to be found in an alpha helix. This is unlikely to be found in an alpha helix or a beta sheet. I did not want you to memorize those numbers, those propensity scores, just as I did not want you to memorize pKa values for amino acids. I will give you pKa values should you need them. And that brings us to our next level of organization, which is the tertiary structure for our protein. The tertiary structure is going to be where our groups interact with one another. We have ionic bonds. We have hydrophobic interactions. We have hydrogen bonds. Those are three of the big ones, but that is going to help a protein fold into a three-dimensional shape. Once a protein folds into its three-dimensional or native state, we can denature it. And we can denature it with things like urea, which is a chaotropic agent. We can use extreme heat, or we can use heat. We can use extreme acid or extreme base to unfold a protein. The one thing that we have to be aware of whenever we're talking about denaturing a protein is we use DTT or beta mercaptoethanol to break disulfide bonds. Disulfide bonds are found between two cysteine residues. That's a covalent bond, so we can't really change the pH and expect that to break. We have to use that unique reagent to break that disulfide bond. Now, tertiary structure was our second to last level. Our last level of organization is the quaternary structure. That quaternary structure, not every protein has a quaternary structure. Only proteins that are made up of multiple polypeptide chains have a quaternary structure. Now, some examples of proteins that have a quaternary structure, or one example of a protein that has a quaternary structure, is none other than our friend hemoglobin. Now, in the event that you think, man, gosh, that guy just talks about nothingness, the last 10 minutes haven't really been nothingness. That's kind of been like the summary of what we've done. So please don't think that's nothingness. It is context. I think it's important to revisit it just to sort of reinforce concepts. I hope that it wasn't too much of a brain drain for you or anything like that. Now, protein function. We were talking about proteins having the function of being able to bind something. Our ligand binding proteins are specifically our oxygen binding proteins. We looked at two of them. One was hemoglobin, the other is myoglobin. Now, we spent a bit of time yesterday talking about myoglobin, and today what we're going to predominantly focus on is hemoglobin. The reason we're going to focus on hemoglobin is because hemoglobin is a really great model for a multimeric protein. Hemoglobin as a multimer, specifically a tetramer, exhibits a phenomenon known as positive cooperativity. That's where one subunit will bind oxygen, and now all of a sudden the affinities that the other subunits have for oxygen, it increases. Now, we did talk yesterday about an oxygen binding curve. The oxygen binding curve for myoglobin is depicted here. Now, there is one extremely important point on this oxygen binding curve. Like if you recognize nothing else on this oxygen binding curve, I want you to recognize this point right here. And I'm specifically pointing out on the x-axis because that point right there on the x-axis is known as the P50. Okay, great. The P50 here is an important point because it tells you the amount of the amount of ligand, the concentration of oxygen that is required to get our protein to half saturation. So that might seem like, well, why do we only care about the halfway point? Well, we care about the halfway point because protein ligand interactions are, and I always like to use this word, they're transient, they're temporary. A protein will bind a ligand and then release it. It's kind of like inhaling, exhaling, which I feel like is a really good metaphor for an oxygen binding protein. Now, that P50 point, one of the important things to remember about this is P50, this is a, or this, if you were to say something like, or if somebody were to say the P50 is 12, I think that it's common to think about a P50 as being similar to a dissociation constant. And whenever you talk about dissociation constants and constants going back to like Gen Chem 2, I think it's pretty common to be like, oh, well, that doesn't have a unit. Now, a P50 does have a unit. That unit is whatever unit is used for the partial pressure of oxygen measurement. More times than not, you're going to see torr. Is that the only unit that you could use to measure the pressure of a gas? Go ahead and add any other unit that you might expect to see with respect to pressure of a gas. While you do that, I'm going to have Rice Krispie treats are considerably chewier than I expected whenever I took the piece of the size that I took. Um, Absolutely. Atmospheres, pascals, kilopascals. These are all great units that you can use that you could see on the x-axis. Now, I don't really like to put that out there and be like, ooh, so you never know what's going to be on your exam. That's that is kind of to me like a silly sort of thing to ask. So you should expect to see on the x-axis torr. That's the unit of gas that I'm going to use whenever I'm using a figure on an exam or something like that. Now, with that said, our y-axis in this case shows our fractional percent oxygen saturation or fractional, yeah, percent occupied. Now, this curve has a unique shape in that it is known as a hyperbolic curve. This is different from what we'll see with hemoglobin, which has a sigmoidal curve. Now, I mentioned this yesterday and I want to double back on it. Um, I want you guys to, whenever I say something like P50 equals, let's go with just this number here, 2.5. I like to pose questions that would be something like, what is the percent saturation of our protein when the O2 concentration or the PO2 is, and I'm going to give you a couple of different options to think about, or a couple of different ways this could be phrased. When the PO2 is 3x P50. Another alternative is, let's say, 20 torr. Now, for this, I want to give you those two options because this 3x P50, well, that's just saying 3 times the P50. Then you would just sub whatever the P50 value is in for that and say, okay, well, I know what 3 times 2.5 is. It's 7.5. So I need to find that point on my graph. Boom, it's right there. And so then the question is, well, what percent saturated is the protein? I'd do dashed lines and I'd say, oh, well, okay, I'm going to say that's 0.7, a rough number. Alternatively, if I gave you the explicit number of the PO2 is 20 torr, then you'd say, okay, well, same thing up here. Oh, that wasn't a straight line. I'm going to call that 0.88. Cool. I want you to understand how to navigate these sorts of questions. Now, with that in mind, the partial pressure of oxygen, the PO2, that can change. The P50, however, is not going to change based on environmental conditions. The P50 will change based on the protein changing. And what I mean by that is if I were to extract or purify hemoglobin from my red blood cells compared to like my wife's red blood cells or something like that, the P50 that my hemoglobin has might be slightly different from what hers has. Now, with that in mind, P50 is something that changes a little bit because when we think about hemoglobin, what changes? The structure of our protein changes. So as that structure changes, that P50 changes. So I know that in the past like 2 minutes, I said, hey, P50 doesn't change. And then I concluded that statement with, but P50 can change. I just want you to think about, well, the environmental conditions are not going to cause the P50 to change. It's not like if you are in a low oxygen environment and then you go to an oxygen rich environment, your P50 changes. Instead, what changes there is the PO2, the O2 concentration in that environment. Okay, so let's see, here we are. We did all this. High P50, low affinity, low P50, high affinity. I always kind of think about that as low P50 is good. High P50 is not good. Now, that's painting with a broad brush, but that's a good kind of general rule of thumb. Okay. We looked at all that. Then we got into this T and R transition. The T state of a protein is kind of your tense state. The R state is your relaxed state. The T state is your deoxygenated form of hemoglobin. The R state is your oxygenated form of hemoglobin. This all takes place because, well, one histidine gets pulled up. And whenever that histidine gets pulled up, an entire helix gets moved. And there we go. We have positive cooperativity. That shows that our hemoglobin protein exhibits a sigmoidal curve. This is kind of our representation of that. At the top here, this is our deoxygenated hemoglobin, has a really low affinity for binding O2. Then down at the bottom, this one that's already bound to O2 is pretty happy to hold on to it. Now, oxygen dissociation. Okay, so that brings us up to yesterday. One important thing about hemoglobin and oxygen binding proteins is we want them to bind it, and then we want them to release it. We want hemoglobin to pick up oxygen from our lungs and take it to our muscles so that our muscles can use it. Now, what we want to know is how these sites fill up and how that varies with oxygen pressure. Hemoglobin's oxygen saturation curve is sigmoidal and not hyperbolic. One of the ways that I always kind of remember that is I think about the letter S, because a sigmoidal curve has more of an S shape than a hyperbolic curve. Now, with that in mind, this equation right here, we need to change in order to reflect the oxygen binding curve or to the oxygen binding trends of something like hemoglobin. Now, we use something known as the Hill equation. The Hill equation shown here reflects the multiple O2s that hemoglobin can bind. Now, with that in mind, HbO2 4 would be our fully saturated hemoglobin because it can bind 4 O2s. Now, when N is called the Hill constant or the Hill coefficient, when N is equal to 1, what you're observing is non-cooperative binding. So this right here, if we were to look at oxygen binding data for myoglobin and we were to try to plot it against this equation right here, well, then we would see ultimately N is equal to 1, where we have non-cooperative binding. Because every individual or myoglobin protein behaves independent of the others. They'll bind oxygen, hold on to it. That's it. Now, when N is greater than 1, you have a positive cooperativity or you have a sigmoidal curve. Now, this right here, this is more or less a model for how hemoglobin works. There are other allosteric proteins that exhibit this same sort of binding pattern. There are, in addition to that, some proteins that display negative cooperativity. That will also show a sigmoidal curve. Now, I want to expand upon these 2 points. And I want to give you an example, or I want to revisit the example of hemoglobin and just say that when one O2 binds, it's easier for the second and third and fourth to bind. Does it, the negative cooperativity? Well, effectively the opposite of that is true. What that means is you would have a multimeric protein that when, and I'm going to switch my terminology up a little bit, when one ligand binds to the protein, it's more difficult for the additional to bind. Okay. Now, I think in principle that kind of makes sense, or conceptually that makes a little bit of sense. But whenever I read that second item, when one ligand binds, it's more difficult for additional ligands to bind. There's a part of my head that just goes to, well, then additional ligands aren't going to bind, and that's all there is to it. And that's not really the case. What that means, think about it like this. Let's say that positive cooperativity, and I'm going to say HB1, HB2. So the first O2 molecule to bind needs, or what hemoglobin needs, is the PO2 of the environment to be, let's just say 10 torr. Okay. So if the concentration of oxygen in the environment is 10 torr, then our first O2 molecule will bind to hemoglobin. Then what we would say is, all right, well, our second hemoglobin will now need, let's just make it simpler, and we'll say 9 torr. So the first one required this minimum threshold, but then the second one's like, oh, well, I'm undergoing a conformational change, so now I need slightly less than you did in order to get it started. What that displays a negative cooperative situation would be, I'm just going to say P sub 1 needs an L concentration. So I'm going to switch it from partial pressure to L concentration of 0.1 molar. Now P sub 2, our second ligand, needs an L concentration, or a ligand concentration, of 0.2 molar. So in order to get the second subunit of that protein to bind the ligand, you have to up the concentration of that ligand. Can I get a number in the chat if that makes sense, or a letter if, wait, I don't follow that? Okay. Okay. So where I'm going with that is, or one way that I could think about it is, um, we'll go back to the junior high dance analogy. I hope that works for everyone because that's my analogy. I don't have any others. If I tried to put one together, it'd be dumb. Okay. So in a positive cooperative situation, the first person gets out on the dance floor when everyone else is like, I don't want to do that. The second person sees that first person on the dance floor and they're like, on second thought, maybe it will be kind of fun. Okay, I'll go out there. In a negatively cooperative situation, that would be like the first person gets out on the dance floor and then everyone else is like, you're not supposed to dance. What are you doing? This is a horrible idea. And so then there would have to be some other sort of intervention to get that second person to dance. Instead, it would be like, this again with an analogy, it would be like, I don't know, somebody comes over the loudspeaker and is like, if you get on the dance floor, I will give you $25. Now all of a sudden the second person is still like, that first person looks like a fool. Oh, awful. But I like $25, so I think I'll go out there. Obviously, we're not talking about paying a protein $25, but instead we're saying, well, there's an increase in ligand concentration that coaxes you into getting on the dance floor. Okay, so if you want to discuss that more, by all means, I'll hang around for a little bit after class. The Hill equation is a little bit cumbersome to work with, and so that's why what I want you to know is these n values and what they indicate for cooperativity. So if I were to ask a question about the Hill equation or the Hill equation, it would effectively be in the event that n is greater than 1, what does that say? Now, with that in mind, there are some things as an instructor where I'm like, I don't want to ask that question because that's such a memorization sort of question and it doesn't really have much critical thinking. So, if I'm a betting person, I'm not going to put a huge amount of money down that there's going to be a Hill equation question. But I do want you to understand positive cooperativity versus non-cooperative versus negative cooperativity. So, if you can work out like a analogy, I mean, no disrespect, but nobody's going to touch that junior high dance analogy. That's like, it's like I'm going to get a back tattoo that explains the junior high dance analogy to positive cooperativity. Um, so anyway, all right. Now I want to revisit this idea of allostery. Allostery is when a protein has effectively two different shapes, the T state or T shape and the R state or R shape. Allosteric means other shape. Now, there are things known as allosteric effectors. Allosteric effectors are molecules or reagents that influence favoring one state or the other. So, binding of an allosteric effector at one binding site affects the binding properties of other allosteric sites or other binding sites. Okay, so let's again go back to hemoglobin or our model for this. So hemoglobin here is displaying a lot of different things. It's explaining protein ligand interactions with a multimeric protein. It's explaining cooperativity or positive and negative cooperativity, but it's also illustrating this concept of, well, you have two different states. Now, with that said, not every protein that has multiple subunits is considered an allosteric protein. But what I want you to know about an allosteric effect or an allosteric effector is something like this. Um, okay, binding of an allosteric effector at one site affects binding properties at another site. Okay, so let me rephrase it. Let me think about that for a second. When our protein binds to a molecule and that causes our protein to now have a different affinity, positive or negative, but a different affinity for binding of another molecule. Now, give me a letter if you say, I don't really follow that at all, or a number if you're like, okay, I see where you're going. I don't know exactly where, but this all adds up. Okay. So if we use hemoglobin, we've primarily talked about hemoglobin binding to oxygen. And whenever it binds to oxygen at one subunit, it undergoes a conformational change. That conformational change leads to other subunits having a greater affinity for oxygen. So, with that, would you agree with me that oxygen is an allosteric effector? A number for, yeah, I'll give you that, or a letter for, I refuse. Okay. So this might sound counterintuitive. It might sound like that can't be right, but oxygen is indeed an allosteric effector for hemoglobin. So I know whenever I first saw this, I was like, oh, well, you've clearly got to be talking about some other compound altogether. No, oxygen happens to be an allosteric effector for hemoglobin. Now, with that said, if we go down to the bottom, oxygen is the ligand, the natural ligand for hemoglobin. It is also an allosteric effector. So we have a term for that. We refer to oxygen in this case as a homotropic effector or a homotropic interaction. Because when hemoglobin binds oxygen, hemoglobin's affinity for oxygen goes up. So oxygen is kind of doing two things. It's the effector, but it's also the natural ligand. It's supposed to be there. Now, with that in mind, there are examples of molecules that are different. And for that, we use the term heterotropic interactors or heterotropic interactions, where the ligand and the effector are different. Okay, so I'm just going to, this is just to throw out an example. This is an incorrect example, or sorry, this is an untrue example, but let's say that glucose is another molecule. If glucose were to bind to hemoglobin and cause hemoglobin to have an altered affinity for O2, then we would say, well, glucose is a heterotropic effector, or it has a heterotropic interaction with hemoglobin. Okay. Can I get a number if you follow that, or a letter if no, that doesn't add up? Okay. Now, what if I were to say glucose binds the hemoglobin, and when glucose binds the hemoglobin, hemoglobin has no altered affinity for O2. So essentially, and I'm sorry for my handwriting there, I was trying to preserve letters, but glucose binding to hemoglobin doesn't do anything for hemoglobin. A reasonable response to that would be, well, glucose is therefore not an allosteric effector. It's not homotropic, it's not heterotropic, because it doesn't do anything to hemoglobin. So I just want to present a number of different scenarios so you don't get tripped up on that or anything. Okay, so I'll scribble that out. So homotropic and heterotropic interactions, or homotropic and heterotropic effectors, are ways in which you can classify allosteric effectors. Allosteric effectors change the nature of the interaction between your protein and its natural ligand. A natural ligand can change the interaction between the protein and the natural ligand. That's a homotropic interaction. A heterotropic is whenever the ligand and that molecule are different from one another. Now, hemoglobin is just a classic example. It's great for this because oxygen does the work itself. It says, hey, I'm supposed to be here. I'm going to cause this change. Now, what are the implications of an allosteric effector? So, the results of binding of an allosteric effector will be seen on an oxygen binding curve or an oxygen dissociation curve. So what we have here are, let's go ahead and look at molecule, or sorry, 1, 2, and 3. Now if you look at this PowerPoint or if you look at this PDF, you'll see there's already some marking on here. And I think that, given enough time, you can process through all this and figure it out. But one of the things that's important to understand anytime we see one of these curves, whether it's this sort of curve or whenever we're talking about enzymes and enzyme kinetics, when you see a curve like this, or like the myoglobin curve, one of the things that's important to remember is this curve is a representation of experiment number 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on. So just as you plotted data and come up with a line of best fit, these lines are lines of best fit. So the curve is not like I know that this was something that I struggled with whenever I saw these for the first time because I was like, oh, I guess what's happening is you put the protein into the tube and then you just ramp up the O2 concentration. Not the case. This one right here, for example, would be a singular experiment where you set up the O2 concentration. And then you look at, well, what percentage of that protein is saturated or has O2? So I just want to bring that up and I'll revisit that later on when we're talking about enzyme kinetics. But that's just one thing to kind of keep in mind with respect to this. So things that and terminology that I want you to be comfortable with respect to these oxygen binding curves is what I mentioned yesterday, kind of briefly. These oxygen binding curves shift to the left or they shift to the right. Now, what can cause these things to shift to the left or shift to the right? Allosteric effectors can cause these binding curves to shift to the left or shift to the right. Now, let's say that we looked at curve number 1 right here, and somebody did all these experiments with O2 and blah, 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 blah. And then we're going to look at curve number 2. And in curve number 2, so let's go with number 1. The experimental design was O2 plus buffer, just to maintain the right pH, plus hemoglobin and everything needed for that hemoglobin. So that's experimental design number 1. You go through, mix these things up and look at, okay, what percentage of this protein is saturated? And you come up with these baseline parameters and you say, all right, well, the P50 is, and I'm going to change this from 1x to, I'm going to say that it's 50 torr. And then the next, and so, okay, well, we got 50 torr. Great number. Neat. Fantastic. Then experimental trial number 2. O2 plus buffer plus hemoglobin. And now I'm going to add another molecule because we're going to see this a little bit later. BPG. BPG is a compound known as bisphosphoglycerate. You don't have to write that down now. It's in a later slide. But what this compound does is it favors deoxyhemoglobin. And when you favor the deoxygenated form of hemoglobin, you're favoring the form of hemoglobin that doesn't want to bind oxygen. So it's almost like you have to compete and negate the impacts of that bisphosphoglycerate. And what you're going to observe is this curve is going to shift to the right. And what does that mean? Well, from 1 to 2, what can you tell me about the P50? First of all, give me a letter if it does not change and give me a number if it does change. Absolutely. Our P50 absolutely changes. Now, a shift to the right or a shift to the left, follow that x-axis. As we move to the right on an x-axis, well, our number is basically 0 to infinity. What can you tell me about the P50? It increases. Our P50 goes up. Okay, so if our P50 goes up, what does that mean for oxygen's affinity? Or, sorry, its affinity for oxygen. Spot on. It goes down. So our affinity for O2 has gone down. So arguably, is bisphosphoglycerate something that if you're climbing Mount Everest, are you like, oh, I got to get some more bisphosphoglycerate? No, we definitely want to avoid that. Now, there's a little bit of nuance to it, and we'll get into that a little bit later, and it's really pretty fascinating. But this shift to the right is an indication that our protein's affinity for oxygen has gone down. And that could be to our detriment. That could be to our peril. Now, anything that lowers our O2 affinity shifts our curve to the right and causes our P50 to go up. And yeah, here we go. I'm just going to jump ahead because the rest of the markings on this slide are all about using that central one, which I've labeled curve number 2, and it says, oh, it moves to the right or it moves to the left. So before I display everything on here, if a move to the right causes our P50 to go up and our O2 affinity to go down, then what do you think a move to the left means? Let's say, moves to the left, what does that mean for our affinity for O2? Our O2 affinity goes up. Therefore, our P50 goes down, which is trying to think of the word that makes me sound fancy. I'm not going to do it. Um, what that does, though, that is in sync with what we've said previously. A low P50, high affinity for O2. A high P50, low affinity for O2. So if our curve shifts to the left, our P50 goes down, our affinity for O2 goes up. Okay, now jump ahead. There we go. Said all that. Okay. Yeah, that's what I want. Sorry. Yeah. Um, Now with that in mind, there are some things that cause the P50 to go down or to go up. I mentioned previously and today, I said environmental conditions do not change um, your P50 or a protein's P50. I need to go back and modify that a little bit because now that I think about it, I'm really only talking about one environmental condition, and that is your O2 concentration. So a change in the O2 concentration is not going to change your protein's P50. However, a change in environmental conditions like pH can change your protein's P50. Now let's think about this. When we talk about our protein going from the T state to the R state, from the deoxygenated form to the oxygenated form, which I'm going to, yeah, there we go. That's what I'm looking for. I want to look at this right here. Um, this histidine that I showed, this one right here. Histidine has an ionizable side chain as an individual amino acid. Within a protein, is the R group of histidine still ionizable? Yeah, why wouldn't it be? The R group is absolutely ionizable. If hypothetically, let's say that the interaction between histidine, this his F8, which is the eighth amino acid in the F helix, if that histidine F8 is, and this is a word that I like to say because I really feel like it makes me feel fancy, is predicated upon histidine being deprotonated. If histidine has to be deprotonated, has to have those lone pairs of electrons in order to interact with that iron, do you think that a change in pH is going to impact that histidine's ability to interact with that iron ion? Absolutely. It absolutely will. So, this is one of the reasons that I spent a lot of time on know your amino acids because those R groups matter. Because here, what we're seeing is hemoglobin, a protein that binds oxygen, that has to transition from this deoxygenated form or its ligand free form to its fully saturated form. Well, there's there we go. That's what I wanted. Um, there was someone who studied hemoglobin's affinity for O2 based on pH. And this is a fellow by the name of Christian Bohr. And what Christian Bohr did was he studied hemoglobin's ability to bind to oxygen under different pH conditions. So he used a couple of different things. He used, well, myoglobin as a nice positive internal control. He used hemoglobin in an environment with a pH of 7.6, 7.2, 6.8. Now, what you can see here is starting from pH of 7.6, we see a shift to the right. So, what does that mean as our pH decreases? And just from 7.6 to 7.2 to 6.8, as our as our pH decreases, our environment becomes more acidic. So, histidines, aspartic acids, their likelihood of being protonated, what's happening to it? Their likelihood or their probability of being protonated is growing up. So if there was an ionic interaction between a glutamic acid that was deprotonated, and now all of a sudden that glutamic acid picks up a proton because the pH has dropped a little bit, that interaction is a little bit less stable. That interaction and the stabilization between those groups impacts something on a broader scale. It impacts physiology. It impacts this person who's trying to inhale and exhale and bring oxygen into all of their tissues. Now, what we see here is we see a shift to the right, which means our P50 is changing. Binding of protons diminishes oxygen binding. Binding of oxygen diminishes proton binding. Now, what Christian Bohr did was he went ahead and he studied this a little bit more specifically. And he wanted to figure out the mechanism for the Bohr effect. Now, this slide right here is a little bit dense. And so we're going to take it piece by piece. And this is definitely going to be, are you with me? Quite often. The pKa's of ionizable groups involved in the favorable ionic interactions are perturbed. Okay, so let's rephrase that. Effectively, important R groups, important ionizable R groups that are involved in ionic interactions in hemoglobin, those pKa's change. This is essentially all that says. That seems a little bit odd. Oh, why the pKa's change? Well, think about it like this. We have an example of two functional groups with slightly different pKa's. And I'm going to reference these two right here. On the left-hand side of the right-hand side of my screen, I've got the amino acid. I'll give you a chance. Single letter code for this amino acid right here. Aspartic acid. Therefore, this one right here, one more try. Boom. Exactly right. Glutamic acid. These two molecules have the same functional groups. but their pKa's differ by about 1. This is about 3.4, and this is usually about 4.3 in that ballpark area. Now, if I were to extend this and I were to say, oh, well, this magic new amino acid's been found and there's, 2 or 3 more CH2s on here, the pKa is going to change. pKa's can change based on the inductive effect. And so when you think about a protein being like a thing that moves, that changes, a pKa changing, I want you to think about that as like maybe not, maybe doesn't happen all the time, but it's possible. It's within the realm of possibility. I believe that it can happen. Now, with that in mind, deoxyhemoglobin, our T state of our protein, has some favorable ionic interactions that stabilize the structure. Okay, so let's think about some candidates that could be involved in these ionic interactions. Well, we can have a positively charged residue like a lysine and an aspartic acid, or maybe a histidine and a glutamic acid. Those are good candidates. And, a positively charged residue and a negatively charged residue. And although these pKa's are, 3.4 and roughly 4.3 each, pKa's can change quite a bit based on an entire polypeptide chain. They can change a little. Now, that's not something that I'm expecting you to be able to calculate. That's something that's empirically or experimentally determined. So, with that in mind, what I'm getting at is if you look at the pKa of, sorry, aspartic acid versus ALD, I'm going to go with ALDI. ALDI is the peptide that I just made. The pKa for this R group right here and this R group right here, they're not going to be the exact same because one is a single free amino acid and the other is within a polypeptide chain. Now, like I said, I'm not expecting you to know what this pKa is versus this pKa. And the reason for that is because that's experimentally determined. But what I'm getting at is this could be 3.4 and this one could be 5.6 because it's in a polypeptide chain, because there is the inductive effect. Can I get a number if, okay, I follow you. I don't know exactly where you're going, but I follow you up to this point, or a letter if stop the press. Okay, great. So we've got some ionic interactions that stabilize the structure, stabilize the T state. So give me a number if you agree with the idea that if we can disrupt those ionic interactions, then we can grease the wheels towards transitioning to the R state. Great. I didn't give you the option of give me a letter if you don't think that. I just decided, no, this is what we're doing. So essentially, if you can disrupt those interactions, then you can move towards favoring the R state and getting this transition to take. Now, with that said, if you somehow fortify those ionic interactions, then you're stuck in the T state. Now, what Christian Bohr discovered was that histidine number 146, specifically on the C termini of the beta 2 subunit, forms an ionic interaction with an aspartic acid, number 94. So we've got this ionic interaction, a histidine and aspartate. Okay. Now the ionic interaction stabilizes the proton against dissociation, increasing the pKa. Okay, so we've got this effectively being positive and this being a nice negative. That interaction right there makes this protein say, well, we're happy. We're protonated. I don't want to give that up. And so the pKa is going to go up. And so the likelihood of that being deprotonated is a little bit low. So this interaction right here stabilizes the T state. Now, with that said, just as a little bit of an aside, if you were to sequence the hemoglobin that's in my cells versus the hemoglobin that's in, someone who lives on the other side of the world cells, you're going to find some differences because, well, unless they're like one of my relatives, which would be unexpected. Just thought of what are the chances you'd sequence these two proteins. Um, let's say that you sequenced this other person's hemoglobin and you found that in position number 146 on the beta 2 subunit of their um, hemoglobins, rather than having a histidine, they had let's go with something, let's go with a serine. So let's think back for a second. They've got a mutation. Serine replaces that histidine. Is serine positively charged? Is it a polar positive? Nope. So is there going to be an ionic interaction between serine at this position and aspartate at that position? No. So will that person's hemoglobin have a stable T state? No. Dang. That person's just living large. They're walking around. They don't have T state hemoglobin. They're like, I'm living in our state world. My hemoglobin's more than likely going to be fully oxygenated. Now, the implications of that are a little bit complicated, but what I want you to think about here is these mutations and the interactions that are disrupted. Like when we were talking about tertiary structure, I wasn't doing that just to be like, well, remember, this is a hydrophobic interaction and this is an ionic interaction. I want you to try to draw the connection between, well, this residue is positively charged, this is negatively charged. Oh, that stabilizes this form of the protein, which is kind of where we are right now. So to bring it back to where we are, histidine and aspartate, a positive residue and a negative residue. That interaction is stabilized and favors and causes the protein to favor the T state. Now, oxyhemoglobin, upon binding of O2, the favorable ionic interactions are disrupted. Aha! So when O2 comes in, it's almost like surgical and it says, I don't like that His 146 aspartate 94 interaction because it's undermining my ability to get my friend's oxygens to bind. I got to get rid of that. Now, His 146 is deprotonated in oxyhemoglobin at a normal blood pH of 7.4. So let's imagine if our pH goes down. And this is like we got to zoom out for a minute. We went really detailed, or we were at this level, then we were really detailed, and now we got to go back out here. We know that His 146 and aspartate 94, that's got an ionic interaction going on. And if O2 binds, well, then that's going to disrupt that interaction. But we also know that if that interaction, that ionic interaction, is stabilized, how would that be stabilized? Well, it will be stabilized by that histidine staying protonated. How can we kind of ensure that that histidine stays protonated? Well, by putting more protons into our environment. How do we make more protons appear in our environment? By having a more acidic environment. Can I get a number if, okay, I follow, or a letter if, wait, come on back. Okay. If I had a recommendation for this slide and these slides relating to the Bohr effect, I would go back through it a couple of times because this is kind of like a chicken and egg situation where it's like, Ionic interaction favors preventing oxygen binding, but then if oxygen binding takes place, then the ionic interaction is lost. But how did that happen if this is so? Just be patient with yourself and look through this a couple of times. Now, the effect of pH on His 146, high hydrogen ion concentration or low pH, favors the protonation of His 146. When His 146 is protonated, the T state is favored. The T state favors the release of oxygen, and anything that favors the T state lowers O2 affinity. Okay. So, at the center of what we're talking about with respect to hemoglobin and binding oxygen, histidine, that His 146 is an important player. It's also important to remember, I told you guys I didn't need you to remember or memorize pKa values, but histidine, to be completely honest with you, histidine has a pKa of our R group pKa of about 6.1. That's one that I've remembered because of the fact that that means where can histidine have a buffering range? Histidine's buffering range can be as low as 5.1. Oh, neat. That's neat. That's acidic. Or it can be as high as 7.1. Oh, a neutral pH is 7. Aha. So histidine is our only amino acid that can buffer or act as a buffer at a neutral pH. So what that means is if you were to shrink yourself down and swim around in a cell and look at histidine residues. Let's look at histidines and aspartic acids on any number of different proteins. You're shrinking, you're flying around in a cell, and you're at a pH of 7. Histidine residues, I'm going to put a check mark by them because chances are a good number of them are going to be protonated because it's got a pKa of about 6.1. Aspartic acids with a pKa of about 3.3, we'll say, the likelihood that an aspartic acid R group is going to be protonated at a neutral pH, super low. Does that mean that it's never going to be? No. It just means it's unlikely to be protonated. So histidine at a neutral pH or at a physiological pH can be protonated and can be deprotonated. So what does that mean? Well, that means that it can participate in ionic interactions, but it also can be a great player in hydrogen bonding. I bring this up just to stress that if there's one amino acid that we will talk about quite often, it is going to be histidine because it can be protonated at a neutral pH. It can be deprotonated at a neutral pH. So that means it can act as an acid by donating a proton, or it can act as a base and accept a proton. Okay, so we'll get more into histidine kind of generally a little bit later. Right now, I want you to focus on His 146. It has an ionic interaction with an aspartate, number 94, and that combination favors the T state or the deoxygenated form of hemoglobin. Now, His 146 is not the only residue responsible for the Bohr effect. The mechanism also impacts other residues. So if we look here, this is just showing some of the interactions that are taking place between other groups on hemoglobin, other contacts within these different subunits. Now, so what you can take away from this is that a proton arguably is an allosteric effector because a single proton can bind to hemoglobin and favor the T or the R state, or loss of a proton can favor the T or the R state. So we've got two allosteric effectors, one homotropic, that being oxygen, and the other being heterotropic, a proton. Now, carbon dioxide is another allosteric effector. Why is carbon dioxide an allosteric effector? Why carbon dioxide? Why is that? Well, carbon dioxide does two things. Carbon dioxide diminishes oxygen binding by increasing the pH. Okay, increasing the pH, or sorry, decreasing the pH. I was reading this line and the next line simultaneously. Decreases the pH, therefore it increases the Bohr effect. So CO2 diminishes oxygen binding. I'm going to put a little star by increasing hydrogen ion concentration. Okay, it decreases the. I'm going to actually not put a star. I'm going to put that in parentheses. So it increases the effect of the Bohr effect. Now, part of respiration is the production of CO2. That's cellular respiration, breaking down sugars. You're going to make CO2 from a sugar as you break it down. The CO2 diffuses from the tissues to the capillaries. Now, how that happens is with the help of an enzyme that we'll look at in just a little bit. That hydration of CO2 in tissues and extremities leads to proton production. So there's an enzyme known as carbonic anhydrase. And here we go. We're going to come back to this in just a second. That's kind of leading ahead. The hydration of CO2. So when water reacts with CO2, it's going to produce, well, it's going to produce all these things on one line. Rats. This needs to be up here. Equilibrium arrows. So CO2 plus H2O is going to produce HCO3 or bicarbonate and a proton. So simply by making, because CO2 is not particularly soluble in a solution, so it has to react with H2O in order to produce HCO3, which is more soluble. This proton right here, what's that going to do? That's an increase in our hydrogen ion concentration. That is going to increase our Bohr effect. So CO2 reacts with H2O to produce this output, or this outcome. In addition to that, hemoglobin acts as a CO2 transporter. So we typically only think about hemoglobin as a O2 transporter, but lo and behold, it can also be a CO2 transporter. I'm going to come back to this point after our next slide. This is the hydration of CO2. The enzyme carbonic anhydrase speeds up this reaction. This spontaneously occurs, but the enzyme makes it go a little bit easier and a little bit faster. CO2 plus H2O yields a proton and HCO3. This figure right here, there's a couple of things to process about it. And this is one of the challenging parts about biochemistry. When you get a figure like this and you see, oh, there's all of the information that I possibly need. This is delightful. Don't get overwhelmed because it is so easy to. You have to start in one place or start somewhere on it. In the top of this, what we have is our tissues, our respiring tissues. What those tissues are going to do is they're going to produce carbon dioxide. Now, that carbon dioxide is going to enter an erythrocyte that is going to take CO2 and H2O and produce HCO3 minus, that bicarbonate. Here's our hydrogen ion that has increased. And ultimately, that's what we're going to have to deal with. That bicarbonate is going to be transported out into the blood plasma. It's going to be much more soluble. So in this case, what we're talking about is carbon dioxide. So what is this?
Diet Mountain Dew.
Oh, Diet Mountain Dew. Sorry. I just got a Diet Mountain Dew delivery. I don't know why I got Diet Mountain Dew, but I did. So it's free. Thank you. Well, it's not, no, it's not free. Effort free, because it was brought to me. Perfect. So that was my wife, not the Diet Mountain Dew delivery system that I have and no one else has. Okay, sorry. I'm checking. Okay, it's 3:11. We're good. 3:11, the band. And it's 3 p.m., 3:11 p.m. Okay. So what carbonic anhydrase is doing is it's basically saying, oh, you're producing a bunch of CO2 because you're going through aerobic metabolism to break down sugars. We've got to deal with that CO2 waste product. So what we're going to do is carbonic anhydrase, I am going to help to make this HCO3, which goes into a solution. You can get transported through your bloodstream from your toes. And that's great because when it gets into your bloodstream, it's got a fate of your lungs. When it gets to your lungs, then this HCO3 from your bloodstream goes into another erythrocyte where, lo and behold, carbonic anhydrase can do the reverse reaction, convert the HCO3 to this less soluble gas, CO2, which then can be given to plants. Okay, so carbonic anhydrase is helping to solubilize CO2, but what it's also doing is it's causing the hydrogen ion concentration to increase, causing the pH to go down, causing the stabilization of the T state of our protein. Now, the accumulation of CO2 lowers our pH in our blood. The O2 depleted muscles generate lactic acid, thereby lowering the pH of the blood passing through them. So this is kind of a secondary thing that's taking place. These protons are taken up by hemoglobin as that oxygen dissociates. Now, so that's, if we go back to this slide, that is number one. So this next slide that I'm going to show you is number one. The next slide is item number two. Hemoglobin as a CO2 transporter. As a CO2 transporter, there is a modification to hemoglobin that is done by itself. That is known as a carbamation. What that is that hemoglobin is able to bind CO2. Whenever it binds CO2, well then what we do is, here's our N-termini of HB, of hemoglobin. So this is the protein. So effectively what that means, and the way that I want you to take this, is that we can take a CO2 and basically attach it with a covalent bond to the N-termini of hemoglobin. Now, one thing that I want you to think about with respect to this is, or answer this question. Give me a number if your answer is yes, and a letter if your answer is no. Does CO2 bind in the same location on hemoglobin as oxygen does? A number if your answer is yes, and a letter if your answer is no. It's my rage excitement. You're absolutely right. It does not. Because when we think about hemoglobin binding to oxygen, well, arguably, hemoglobin's kind of not binding oxygen. Only with the help of that heme ring and that iron ion is it binding to oxygen. And, looking closely at this, or even not super closely, this is the N-termini of the protein. This is amino acid number one. I didn't draw heme there. This is what is known as a post-translational modification. I'll just say mod. This is the protein getting some sort of chemical modification after translation has taken place. The modification being the attachment of a CO2 molecule. So carbamation, that's what this is called. A carbamation event causes a proton to be released. That proton being released causes our pH to go, which causes our form of hemoglobin that is favored to be our T state. So the funny thing about this, and whenever I say funny, I'm kind of loosely using that term. Um, both of these things, the carbamation and the basically intervention by carbonic anhydrase, what they're both doing is causing the pH to go down. So our environment becomes more acidic. So CO2, yeah, it's an allosteric effector because whenever it binds to our protein, now all of a sudden it is favoring the T state of our protein or the T state of hemoglobin. Okay, now this reaction aids in the transport of CO2 to the lungs. So HCO3 is one way in which CO2 gets back to the lungs, but then slapping the CO2 directly onto the N termini of hemoglobin also helps CO2 get back to the lungs. It also increases the Bohr effect by releasing hydrogen ions. The bound carbamates can also form ion pairs, stabilizing the T state or the deoxy state, stabilizing of the deoxy state. Okay, now here's our, this slide is basically a summary of what we've looked at a little bit ago. And I'm going to tack with another summary of this tomorrow when class begins. Um, Essentially, we inhale O2, goes into the bloodstream after it binds to hemoglobin. So alveoli in your bloodstream, there's small enough pores in those alveoli that O2 can bind. Hemoglobin goes through the bloodstream, which O2 itself is not very soluble in a liquid. So hemoglobin aids in that O2 becoming soluble. That HbO2 gets to the muscles. That oxygenated hemoglobin drops off that oxygen in the muscle tissue where myoglobin says, okay, I'll hold on to this. Hemoglobin, in its kind of deoxy state, one thing that it does is it goes back to the lungs through the bloodstream so that it can go and pick up more O2 so it can keep this process going. Now, I'm going to erase this because I'm going to go back to that. Our myoglobin that has bound oxygen, it holds on to oxygen, but also it releases it so that we can go through cellular respiration. When we go through cellular respiration by breaking down a bunch of sugars, CO2 is our waste product. That's our end, that's our destination product. That CO2 will react with water with the help of the enzyme carbonic anhydrase. Carbonic anhydrase is going to make some HCO3. That's going to cause the stabilization of our T state of our hemoglobin. That T state of our hemoglobin, or our protonated state of our hemoglobin, is going to go through the bloodstream. And whenever it gets back closer to the lungs, then it's going to release that proton where carbonic anhydrase is going to pick it up, react it with HCO3 or bicarbonate to produce water, but also CO2 that is less soluble and can go and be exhaled also from the lungs. Now, what is not shown in this slide right here is we're not showing the carbamation. That's not to say it doesn't happen, but it's not as big of a factor in terms of transport. In addition to that, this shows, oh, the exact same proton. It's not the exact same proton. So don't stress about that. Just understand that protonated hemoglobin at histidine 146 is going to drop off a proton, or it's going to become its deprotonated form. Okay, so O2 is abundant in the lungs. The oxygenation favors the R state. Oxygenation has the effect of releasing protons. Releasing protons shifts the equilibrium from bicarbonate to CO2 and H2O. And then that CO2 can be expired. Okay. We're doing well. We're good. We're good. We're good. We got 20 minutes. Well, actually, no, I said we're good. Give me a number in the chat if you're good. Give me a letter if there's something that you want me to go back over, or just kind of a preview like, hey, I'm going to hang around for a couple minutes after class. Okay. Okay. This is a lot to process. Be patient with yourselves. And yeah, you're doing good though. Okay, that sounds great. All right. So we've got we've done lots of details about allostery. We've had lots of like we've it's almost like we've cracked open a book about allostery and the details of that. So, kind of put this stuff into perspective. There's a couple of residues that are particularly important, a couple of interactions that are particularly important. But just keep this into perspective as okay, this is just one chapter of the class of biochemistry that we're reading. Now, what happens in the tissue is whenever our hydrogen ion concentration is increased, well, then CO2 is going to be increased. CO2 is abundant and our pH is low in the tissue, and our high CO2 concentration is going to lower our pH. This is going to favor the O2 release by favoring the T state. Now, with that in mind, I want you to become a little bit comfortable using this terminology of favoring the T state or favoring the R state. So think about, well, what things go hand in hand. A T state, well, that is favored when the pH is more acidic. An R state is whenever the pH is more basic. And we're not talking basic like 14, instead, we're talking like 7.6 as opposed to 6.8. The so the formation of bicarbonate or HCO3 minus through carbonic anhydrase is going to release more protons. The reaction of CO2 with hemoglobin releases more protons, and that in effect favors the deoxy state of hemoglobin or the T state of hemoglobin, promoting the release of O2 and binding of CO2. Now, our next allosteric regulator, which if you're thinking, oh, great, we've got 20 more. No, we don't. We've got a couple more slides. This is a 43 slide deck, and then we'll touch on enzymes. Or we'll see. Bisphosphoglycerate. Bisphos. Okay, we got probably two phosphoruses there. You're right. Purified hemoglobin binds oxygen tighter than serum hemoglobin. Why is that? It's because of this compound known as bisphosphoglycerate. I like this model down here in the lower right-hand corner. The reason that I like it is because it shows, well, our phosphorus, our other phosphorus, and our glycerate, our acid. So just to kind of build this molecule up, that right there is a molecule commonly known as glycerol. Now, glycerol, if you replace that OH with OPO3 2 minus, and then you replace this one with OPO3 minus, we've got bisphosphoglycerol. If we replace this, oh, it shouldn't be CH2, it should be CH. If we replace this with carboxylic acid, now we've got bisphospho, here's our two phosphoruses, glycerate as an acid there. So this is bisphosphoglycerate. Each phosphate group has two negative charges. Our single acid there has a third negative charge. I'm going to erase all this because I've got more text coming up here. BPG is a naturally occurring compound in red blood cells. Its purpose is to modulate hemoglobin's oxygen affinity by preferring the deoxy form. BPG binds inside the central cavity of deoxyhemoglobin. It has an overall charge of -5. And those negative charges love to interact with a couple of positively charged residues. 2 lysines, 4 histidines, and 2 N-termini. So those negative charges on this bisphosphoglycerate are just kind of in hog heaven. They're like, this is fantastic. Bunch of positive charges. We love being negative charges. This is great. So they will interact with that. Those are a bunch of stable ionic interactions in the center of that, or in that central cavity. Now, if you remember, one of the things that I asked early on when we were talking about hemoglobin was I looked at the T state here and the R state here. T state, R state. And one of the things that I remember us mentioning and kind of agreeing on was that central cavity in the T state is a little bit larger than in the R state. I always kind of think about bisphosphoglycerate as basically like a wrench in the spokes of the bicycle that is hemoglobin. It just kind of lodges in there and jams that protein all up. It gets stuck in there and it's almost like, well, sorry, hemoglobin, you're not making your transition from your T state to your R state because I'm stuck here. So that's how bisphosphoglycerate is going to stabilize the T state of this protein. Now, with that said, add a number if you think that bisphosphoglycerate is an allosteric effector, and add a letter if you think that it is not. And I'm just going to go back to our definition for a allosteric effector. Jeez, you guys are doing a lot today. There we go. Binding at one site affects the binding properties of another. Okay, I got numbers there. I like it. You're right. It is an allosteric effector. One thing that I know people have gotten mixed up on is they're like, oh, well, it has to bind in the same place as the natural ligand. No, it doesn't. It does not have to. That would be closer to a homotropic effector or homotropic interactor. So bisphosphoglycerate, so we've got a couple of allosteric regulators. O2, protons, carbon dioxide, bisphosphoglycerate. Now, bisphosphoglycerate, by this definition, sounds like, oh, well, it favors the T state. I don't like the T state. I want my hemoglobin to be oxygenated so I can live and walk around. And it's not all bad, though. And we're going to get to it in just a second. But what this right here is showing us is this is showing an oxygen binding curve of hemoglobin in a couple of different scenarios. This band right here, this line right here, is stripped hemoglobin. What that means is that it has no heme, it has no iron. How much oxygen is it going to bind? Well, it's about right here. Or sorry, it has heme, it has oxygen, but it doesn't have anything else. Now, this next line right here. So let's go ahead and look at our P50s. Stripped hemoglobin, P50, I'm going to say that that's approximately, boom, about 10. Stripped hemoglobin's about 10. Our next line, that is the same hemoglobin, but we put CO2 in the environment. And I'm going to call that about, I'm going to just number it 2, 3, 4, 5. Number 2, our hemoglobin plus CO2, actually I'll do this, plus CO2 is going to have a P50 of about 15. And if there's any numbers here that you're like, where's that coming from? Please don't hesitate to stop me. Next, we've got plus bisphosphoglycerate. Oh, that's not plus CO2 and plus bisphosphoglycerate. That's just plus BPG. Our P50 is about, let's say, 22. So that one's done. And then our fourth one right here, I'm going to call that plus BPG and CO2. I'm going to call that about 25. And then last but not least, this red line, that's our whole blood. That's at about 26. So essentially this figure is, hey, let's try to reconstruct or reverse engineer hemoglobin's oxygen binding ability. And we're going to add in piece by piece. We add CO2. What does our P52 or what does our P50 do? It goes up. We add BPG, our P50 goes up. We add BPG and CO2, our P50 goes up. Now, what is whole blood? Well, it's a little bit higher. That to me means that they didn't completely reverse engineer the setup. And instead, you got close to everything, but maybe not everything. Maybe there's something else in the environment or in the whole blood that causes the P50 to go up a little bit higher to 26. Okay, let me just take a look at these last few slides. Okay, good. We've got 3 slides left on this, and then we're going to call it a day. High altitude and bisphosphoglycerate. This slide on the right-hand side, it's a little bit complicated, or this graph on the right-hand side is a little bit complicated. Atmospheric pressure decreases with altitude. So effectively, your partial pressure of O2 is going to decrease. Short term, increase in the production of bisphosphoglycerate. Under normal conditions, your delivery of oxygen is about 38%. So what that means is that if you've got fully saturated or fully oxygenated hemoglobin in your bloodstream and it goes to the tissues, about 38% of the oxygen that gets to your tissues gets dropped off. So what that means is that individual hemoglobin proteins, they're not all coming back with no oxygen whatsoever. So it's almost like I always kind of think about it as the oxygen coming back to your blood looks a little bit like this. You've got HbO2, some with two oxygens, HbO2, some with 3 oxygens, and then maybe there's a couple that are HbO2 1, and then last but not least, you're going to have a mixture of all of them. About 38% of the oxygen that gets to your lungs gets dropped, or gets to your tissues gets dropped off. Now, that's under your normal conditions. Okay, so effectively what that means, when you're at sea level, you get as close to 100% saturated as possible because the O2 concentration is high enough. At sea level, the O2 concentration in the atmosphere is about 100 torr, and that's good. What this is showing is that your venous your venous hemoglobin right here is coming back with about 38% less oxygen than whenever it started. Does everyone follow that? Now, this is significant because when you're under low atmospheric conditions, the O2 concentration in the atmosphere is right about here, 50 torr. So what does that mean? That means that when you're outside breathing at 4,500 meters, which would be, let's see, that's a little bit more than 2.5 miles up. So it's definitely higher than Denver. You're at about 2.5 miles above sea level. When you're there, your O2 concentration in the atmosphere is lower. And so when you're inhaling, you're only getting about, call that 90% of the oxygen that you would get at sea level. In which case, sometimes you might get sick. Sometimes you might not be able to run as fast or walk or as far or anything like that. You're going to have a physiological impact. Now, what that also means is that only your muscles and your tissues are only getting about 30% of the oxygen. So when they're accustomed to getting 38% of their oxygen dropped off, they're seeing a loss of about 8% less oxygen getting to your tissues, which is maybe one of the reasons that you kind of get sick. Now, bisphosphoglycerate. I got to be honest, I've kind of been painting it into a negative light and thinking like, oh, bisphosphoglycerate's bad. It's not. The reason that it's not bad is because whenever you are at an elevated atmosphere or elevated altitude, your bisphosphoglycerate is going to cause the P50 of your hemoglobin to shift, or this oxygen binding curve is going to shift to the right, which is going to put you in a position where, well, it's going to take a little bit more to get you to full saturation. But the important part of this is bisphosphoglycerate is going to enable, with that elevated concentration of bisphosphoglycerate, it's going to enable the hemoglobin that's circulating in your bloodstream to drop off 37% of the oxygen that basically you're taking on. The key here is at sea level, 38% of the oxygen that you bring in gets deposited to the cells, gets to your muscles. 38% gets to the muscles. Okay, so the muscles, think about this as muscles are happy when they get 38% of the oxygen that you bring in. Well, when you go up to an increased elevation, those muscles are only getting 30% of the oxygen that you bring in. But when bisphosphoglycerate concentrations go up, now all of a sudden, bisphosphoglycerate helps you deposit or deliver 37% of the oxygen that you bring in. So effectively, bisphosphoglycerate almost acts similar to, bisphosphoglycerate basically acts to make your muscles think that, hey, we're at sea level. Because don't worry, you're getting 37% of the oxygen that we're bringing in. And the muscles are like, well, we're accustomed to 38. And bisphosphoglycerate says, well, the best I can do is 37. And that's better than 30%. Okay? And then the muscles say, okay, that's a good point. Okay, so bisphosphoglycerate does aid. Now, next up this is just kind of a general overview of oxygen binding curves. We will shift to the left or we will shift to the right. When we shift a oxygen binding curve to the left, well, what are some things that make that take place? One thing is our P50 is going to go down. Binding of O2 causes a shift to the left, I'm sorry. Binding of CO2, protons, or bisphosphoglycerate cause a shift to the right, shifting to the T state and shifting to the release of O2. Now, in a more basic environment, or binding of O2 causes a shift to favor the R state, which is a shift to the left. This gamma hemoglobin, which is what I'm going to leave for tomorrow, which our very last slide, fetal hemoglobin, I'm going to stop here because that very last slide, that's what we're going to tackle tomorrow. And then we're going to talk about enzymes. So what I want you to take away from today is we talked a lot about allosteric effectors. This slide right here, if you're like, I've got to learn one slide and I can expand on it, this is the slide to go after because this captures everything. This captures the biggest points of today. CO2, bisphosphoglycerate, protons, all of those things cause a shift to favor the T state, our deoxygenated state. Everything else causes a shift to the left, which favors our R state. And each one of these things, there's a lot to unpack. But be patient with yourself, work through this deliberately, and I think you're going to be in good shape. I'm going to stop my recording. I'm going to be around. So I will stop right now. I hope you have a great